All right, I'm so sorry for the break in transmission, very due to technical issues. Yeah, so we just finished talking about the moon phases in the last video. So let's move forward to see what else we have. We almost wrapping up here. So next we talked about eclipses, and we said that eclipse by the very definition is when something obscure another object from receiving light. In other words, something comes in between the journey of the light towards another and then blinds it, or the shadow of it falls on the other object. So simply put, a solar eclipse is when the moon blocks the light that is coming from the sun and the shadow of the moon falls on parts of the earth. Then we call this a solar eclipse. Now note that for a solar eclipse, it is SME, which means the M always has to be in the middle. The moon has to be in the middle. Generally speaking, is the new moon phase, or the new moon phase. That is where a solar eclipse can happen. And then we say there are two kinds of eclipse. We have the total eclipse and partial eclipse. Total eclipses is when the darker shadow, which is the one you call the umbra, falls on that part of the earth, then you experience a total eclipse. So for instance, the part of the earth that is around this dark shadow, we experience a total solar eclipse, and that is caused by the umbra shadow. Then you have the lighter shadow, which is the penumbra, and that area of that part of the earth experiences partial solar eclipse as well. So important you note that the moon always has to be in the middle, and one is total eclipse, the other is partial eclipse. One is caused by the umbra shadow, the other is caused by the penumbra shadow. Next is the lunar eclipse. Lunar eclipse is the earth that is in between the sun and the moon. So it is the moon that is being obscured from receiving the sunlight. So when the dark shadow of the earth falls on the moon, then you have a total lunar eclipse, and the moon will be red in most cases, and we discuss why. It's called the bloody full moon. So that position of the moon is the full moon when the moon is in that position. Then when the moon is on the lighter shadow of the earth, then you have your partial eclipse caused by the penumbra shadow. What important thing could we be forgetting here for eclipses? Yeah, I think that's basically it. Solar eclipse and lunar eclipse, both of them can be partial, both of them can be total as well. Good. Next, we went into geologic history. Almost a lot to talk about it, but if you understand page 8 and 9, then you know already how to use this very well. And we say that geologists and scientists group the entire Earth's history using this geologic history table here. The largest time frame is the eon. Then eon is divided into era. Eras are divided into period. Periods are divided into epochs, and epochs are the smallest time unit for now, at least for this level. Then the next column talks about life on Earth, which means the various fossils and the various life form, whether plants or animals, that existed throughout the different times of the Earth's history. And then next is the time distribution of fossils, which means what time a particular fossil appeared and what time they got extincted for some reason or another. And using the bar, you should be able to tell when the animal first appeared using the letter, and you should be able to trace it. And each of these letters represents each of these index fossils that you have at the bottom of the ESRT, page 8 and 9. All right, so both time distribution of fossils and life on Earth talks about things that have life that existed on Earth, still existing, or how they evolved, or when they first appeared on Earth. The last two columns, important geologic events in New York and the inferred position of land mass, are inorganic events, which means they are processes that does not have to do with life or life form on Earth. These are things that has to do with maybe deposition or creation of landform or continental drift or shifting of the continents. All those geologic landform events. That is what this last two row or last two column addresses. So we talked about orogeny. Orogeny is another way of saying mountain building, when continents collide together and build continents and build mountains. Then lastly, index forces all the way at the bottom. Each of them have a unique letter, and those letter you can use to trace when they appeared and when they got extincted in the time distribution of fossils. Also, don't forget, whatever is at the bottom is older than whatever is on the top. So the more you go deeper to the bottom, the more you are going back to the beginning of the Earth. And then on top is the more recent events that are happening right now. What else? I think that's pretty much it for this graph. Hope that does justice to it. Then we also talked about half-life, remember? And we said half-life simply means half, which means how long it takes for a radioactive isotope to become stable or to decay to half its size. So when a radioactive isotope is 100%, everything about it is 100% active and is exposed, then it starts to decay, or it starts to disintegrate to a more stable version. And the amount of time it takes to get to half of its original volume is called half-life. So if it has 100% initially, how long does it take to get to 50%? We give you the first half-life. Then how long it takes to get from 50% to 25%, which is half of 50, that is your second half-life. And then of course, half of 25 is 12.5%, that will be your third life, on and on like that. So half-life simply means how long. Is a measurement of time. It's not a measurement of quantity, it's a measurement of time. All right, how long it takes to get to half. Okay, so from 100% you get to 50, 50 to 25, 25 to 12.5, 12.5 to 6.25, 6.25 to 3.125, thereabout. So you get the point. You are always dividing by 2. So if you have a written question and it's ask you what is the first half-life, since it said first half-life, it means you only need to divide by 2. If it asks how many percent is remaining after 3 half-life, it means you divide by 2. Whatever you get, you divide by 2 again. Whatever you get, you divide by 2 again. So you divide by 2 3 times, because the question says 3 half-life. So whatever the number of half-life the question is asking or probing you, that is how you're going to divide by 2 until you get to a definite answer. Yeah. Okay. Another way that they can also pose the question to you is by giving you a graph. So they can give you a graph. All you have to pay attention to is to see what is on the y-axis and what is on the x-axis. On the y-axis here, for instance, you can see that it's in percent, and currently it's at 100%, and it has 10 grams. All right, so there are 10 grams. So at that 10 grams, it's at 100%. So when it undergoes its first half-life, so first half-life will be 100 divided by 2, and that will give us 50. So by the time it gets to 50, then the 10 grams would have gotten to 5 grams, because it's going to get to half, how long it takes to get to half. So half of 10 is 5, half of 100 is 50. So you get a point. All right, so half of 100, 50, half of 10, 5. Then by the time of the second half-life, then 50 divided by 2 will be 25, and then it will be half of 5, which is 2.5. And then the third half-life, which will be 12.5, that will give you 1.25 kg, and you get that by dividing 2.5 kg by 2. And then by the end of the fourth half-life, you have 6.25%, and that will give you 0.625 grams. So all you have to do is divide the number of grams by 2, get 5, divide by 2, 2.5, divide by 2, 1.25, divide by 2, 0.625, and then the next one you just keep dividing by 2. That is what half-life simply means, divide by 2, and then you read the information from the question. So if the question says how many grams remains after the first half-life, all you have to do is know that the first half-life will be 50, because from 100 divided by 2, then that's your first half-life. So how many grams will remain? You just go there and you read it off. All right, and then the number of half-life is indicated here, 1 half-life. So again, all you have to pay attention to is what is on the x-axis and what is on the y-axis, and then look at the graph and then use the graph and the information given to you to deduce your answer to the question. Okay, next we started discussing about minerals, and we say for something to be considered a mineral, it has to have 5 characteristics. The first one, it must not be man-made, which means it is natural. It occurs in nature by itself. It is not created by man. Next, we say it must be inorganic, which means it must not come from something that has life or something that was once alive. Okay, so it has to be inorganic. Then next, we said it must be solid. It must not be liquid. It must not be gas. Next, we said it must have a definite crystal structure, and then it must have a definite chemical composition. Those are the 5 characteristics that would make anything to become a mineral. So going by these characteristics, things like coal, for example, or things like sedimentary rock or bioclastic sedimentary rock or organic sedimentary rocks, they are not considered minerals because they came from things that once had life. They came from the shells of animals that are dead or trunks of trees that are dead. So in that way, they are not inorganic. The gas that we use to cook cannot be considered a mineral because it is a gas. Minerals has to be solid. So take note of all these 5 characteristics. Occur in nature, must not be man-made, must not be organic, which means it has to be inorganic. It must not be liquid, must not be gas, it has to be solid. Then it must have a crystal structure, and they must have a definite chemical composition. Then we started looking at properties of various minerals and how we can use those properties to identify those minerals. We did a lab on this. We talked about luster. Luster simply means how does the mineral shine? Does it shine like a coin? You know, like your quarter? Does it have a metallic luster like this guy? Or does it not? If it has, or it shines, or it looks like a metal, then definitely the luster is metallic. If otherwise, then it is non-metallic. Next is hardness, and we can measure hardness by scratching the mineral against glass. Glass has a hardness of 5.5. So if the mineral scratches the glass, then the mineral is harder than the glass, which means the hardness of that mineral is more than 5.5 because it scratched the glass. But if the mineral did not scratch the glass, it means the mineral is soft. It's way softer than the glass, which means the hardness of that mineral has to be below 5.5. Next, we talked about color. Then we talked about streak. Streak is the color of the powdered mineral. So you take the mineral and you rub it against the porcelain plate or against the streak plate, and then you see the powder that it produced. The color of the powder is what is called streak. Then lastly, we talked about breakage, which means how the mineral breaks. So minerals, when they break, they form real rough edges, all right? Real rough, irregular shape. So those kind of breakage, they are called fracture. While some minerals, when they break, they form smooth surfaces, or they form perfect angles, or angle 90, they form regular shapes. Whenever they break, they form that regular shape, or they open like pages of books, or they form smooth flat surfaces, horizontal surfaces, or well structured and well angled edges. So those kind of minerals, they are that kind of breakage is referred to as cleavages. All right, so cleavage breaks smooth, regular angles, regular shape, parallel, smooth, while the other one, irregular, is called fracture. Okay, and your ESRT page 16, the last page. So this should be able to, you should be able to use this. Luster, how it shines, hardness, if it can scratch a glass or not, and then you have your cleavage. It can either have a cleavage, which means it breaks regularly, or it produces fine smooth surfaces or regular angles, or fracture, which means it breaks and becomes very, very irregular. And then you have common colors here, distinguishing characteristics, and then the uses, never forget that. So that will help you to see to answer some recent questions when they say a particular mineral is used for one stuff or the other. Then composition, these are the different chemical composition that we just discussed about. Minerals must have a definite chemical composition. All right, if you are confused about any of those symbols, you can use the stuff at the bottom. All right, that gives you what each of those symbols means. For example, Al means aluminium, Fe means iron, K means potassium, Bp means lead, on and on like that. And then of course the last column talks about the name of the mineral. Pretty easy ESRT page to read. I mean, we did a lot of practice on this. Okay, next we discuss rock circle, and we said there are three kinds of rocks. You have the sedimentary rock, you have the metamorphic rock, and then you have the igneous rock. All right, igneous rock forms from cooling and solidification of molten magma. Sedimentary rock from evaporation or precipitation or the accumulation of sediments, and metamorphic rock happens as a result of heat and pressure. So these rocks can transform to one another through various processes. So it's important you know that the guys in the rectangle, those are the names of the types of rocks that we have. Then all these other guys that are in between are the processes that produces each of those rocks that I just mentioned. For example, to produce a metamorphic rock, that rock must undergo heat and pressure. That is what a metamorphism is all about. So for a sedimentary rock to become metamorphic, it must undergo heat and pressure. For an igneous rock to become metamorphic, it must still undergo the same heat and pressure. All right. For anything to become an igneous rock, it must undergo melting to form magma. Sedimentary rock must undergo melting to form magma. Metamorphic rock must undergo melting completely to form magma, and then that magma is what cools down and solidifies to form the igneous rock. And then for any of these rocks to become sedimentary rock, they have to be broken down into smaller pieces. They have to be broken down to form sediments, and it is those sediments that are accumulated, buried, deposited, compacted, and cemented and solidified to become sedimentary rock. So it's important you take note of all the processes that produces each of those rocks that I just mentioned. What else is important here that I should review? I think that's it. Let's move forward. Okay, so here just kind of throw more emphasis on how each rock is formed. Igneous rock, like I just mentioned moments ago, these are rocks that are formed from molten lava or molten magma that are ejected into the earth. Now, some of them can get trapped below the earth. Those are called intrusive igneous rock because they did not make it to the earth's surface. While some make it to the earth's surface as volcanic eruption, so we call those ones extrusive igneous rock or volcanic rock because they made it to the earth's surface. So intrusive and extrusive igneous rock from cooling and solidification of magma. Metamorphic rock, on the other hand, is rocks that have undergone intense heat and pressure. So imagine having all this solid rock on top of you. It will just squash you, it will squash things. So when things are heavy, they squash and they put things under enormous pressure. So that is the pressure that creates metamorphism when you have too much weight on you, or the forces of nature that are pressing against the object forces the rock to undergo changes. Another way it can undergo changes is via heat when it's pushed all the way to the bottom, or when lava or magma comes in contact with them and then it metamorphoses them. So metamorphic rock is formed from heat and pressure, and you often identify metamorphic rock by it has mineral lineation or bending, most of them. We'll talk more about that when we get to the ESRT version of it. While sedimentary rocks are rocks that form from when every other rocks break down into pieces, and those breaking down is being transported from the top of the mountain and then being taken down to the stream, and then all the stream deposits them here at the beach. That's why you have a lot of sand at the beach, and then more are deposited under the ocean, more are deposited deep in the ocean, and they are accumulated over a long period of time, thousands and thousands and millions of years, and then over time produces rock in different layers, and sometimes preserving different life forms that are existing at the bottom of the ocean or that are existing on land. So sedimentary rock preserves them. So sedimentary rock are produced from the sediments of other rocks, small particles of other rocks that are collected and buried and compacted and deposited over a long period of time in layers. Yeah, that is that. So that brings us to our ESRT for igneous rock identification. These are the names of all the igneous rock that you are going to be dealing with for high school. And then you should be able to group them into intrusive, which is plutonic. These are rocks or igneous rock that stayed underneath the Earth's surface. Then extrusive, these are volcanic rock that made it to the Earth's surface. Important you pay attention to the line that separates them. So granite is intrusive, rhyolite is extrusive. And because extrusive igneous rock comes in contact with the air, sometimes they could have gas pockets, also known as vesicular. And extrusive igneous rock cools down fast. So because of the result of their fast cooling, they don't have time to produce crystals. So they end up having smooth or tiny grain size. So as a result, those are cooled down real fast. They are glassy. You know, they produce like, it's just like a glass. Or they are fine, very small crystal size, less than 1 mm. You know, when you look at the size of the crystals. All right, so that is what extrusive igneous rock looks like. However, intrusive igneous rock, they got trapped below the Earth's surface, so they don't cool down fast because the Earth's surface acts as a blanket that traps the heat from the lava, so they cool down slowly. As a result of that slow cooling, they have time to form large crystals. So you see their crystal size ranging from 1 mm to 10 mm or even larger than 10 mm. Those kind of texture, they are either coarse or very coarse. And because they don't come in contact with air, they cannot have gas pockets. So they are non-vesicular. Make sense? Yeah. Next, we talked about the whole concept of mafic. Mafic rock are very high in density and they are dark in color and they are rich in iron and magnesium. While the opposite is true for felsic rock. Felsic rock, they are rich in silicon and aluminum, lower in density and lighter in complexion. So all the rocks that are here, all right, obsidian, pumice, rhyolite here again, and granite and pegmatite, all these rocks are felsic. While this rock on the right side, basaltic glass, scoria, vesicular basalt, diabase, gabbro, peridotite, and dunite, they are all mafic because they are on the right side. Why these 1, 2, 3 guys? They are confused. They are just in between. All right, they neither fall on mafic or they neither fall on felsic, so it's important you grab that concept as well. Then you also have to know the mineral content that each of these rocks contain. Remember, minerals come together to form rocks, so rocks are a collection of different minerals. So for example, granite has potassium feldspar, has quartz, has pacloclase feldspar, then has biotite, and have amphibole. So all these rocks are present in pegmatite, granite, rhyolite, vesicular rhyolite, pumice, and obsidian. On the other hand, rocks such as dunite only have one mineral. Now, those kind of rocks, they are called monomineralic because they have only one mineral. Peridotite has 2 minerals, so when you draw it all the way down through the middle, you see the pyroxene and then you see the olivine. So it only has those 2 minerals. All right, pay attention to the broken line as well. Why all these guys here have these minerals at the bottom, that is feldspar, pyroxene, olivine, and amphibole. And then a little bit of biotite if you look, so because the broken line cuts through in that way also. Pretty much that's it for our ESRT for igneous rock. Next is the ESRT for sedimentary rock. Pretty easy to read. You have the texture, you have the grain size, composition, comment, rock name, and symbol. Really important to pay attention to the symbol. Now we all know that igneous sedimentary rocks are of 3 kinds. All right, igneous rock are of 2 kinds. Igneous rock is intrusive and extrusive. Sedimentary rocks are of 3 kinds. You have the inorganic, which is the clastic sedimentary rocks. These are rocks that are formed from particles of other rocks, sediments of other rocks. Then you have the chemically formed. These are rocks that are formed from precipitation and evaporation. These are rocks that are formed from chemical processes. So they are called chemical or crystalline sedimentary rock. Chemical or crystalline sedimentary rocks. These are rocks that are formed from precipitation and evaporation. Then lastly, you have the organic or bioclastic. Once again, once you hear the word organic, it comes from organisms. Once you hear the word bio, it comes from something that once had life, plants and animals. So these two rocks at the bottom here, they are bioclastic sedimentary rock because they came from things that once had or once existed or once had life. So those are the three kinds of sedimentary rock. And then every other piece of information you can also deduce from this ESRT composition. That is what they are made up of. And then comments, it's just different things that distinguishes them. And then common mineral names and rock symbol as well. All right, whenever you are dealing with any question that has to do with grain size, pay attention to the number of zeros to the decimal places. That should also help you in answering those questions. And then whenever you see a question that has to do with accumulation from things that were once existing, like plants or like trees or like animals or the shells of animals, then you should know you are really dealing with bioclastic or organic form sedimentary rock. All right, next is metamorphic rock. Easy to read as well. We say that metamorphic rock, because of heat and pressure, they get foliated. By foliated, we mean the minerals form lines, they form mineral alignment, or they form that bending, that wavy, swiggly kind of movement or kind of alignment, if you will. So that is called bending. So all these kind of metamorphic rock are referred to as foliated, which means they have pattern like a zebra. Yeah, what's the other word you guys use during class? I know someone mentioned zebra, someone mentioned check, I don't know, but you get the point. Then grain size tells you if it's fine, if it's medium, or if it's very coarse. Composition tells you the mineral that each of them have. Pay attention. Slate only has one mineral. Phyllite only has 1, 2, 3, 4, 5 minerals. So pyrite does not have pyroxene because pyroxene did not get up to phyllite. So it's important you understand that as well. Then for the ones that are below, you can see that most of them are like kind of monomineralic. Either they have only one mineral, carbon, or various minerals to specify. That should give you an idea. Then metamorphism, or the kind of metamorphism that produced the rock. You have regional metamorphism. This is metamorphism taking place over a large portion of the earth. And then you have contact metamorphism, when igneous rock is trying to, or when lava injects itself through the earth trying to erupt, and then as it's injecting itself, whatever it comes in contact with, it changes it and metamorphoses it. So that's called contact metamorphism. So the lava has to come in contact with the rock in order to change it or metamorphose it. That kind is called a contact metamorphism, while the other type is regional metamorphism. And then also take note of their rock names and symbol as well. All right. The comment section also tells you the name of the parent rock. Okay, for instance, slate is produced from shale. All right. Anthracite coal is produced from coal. Hornfels is changed from heat and pressure and lava. All right. Quartzite is from sandstone. Marble is from dolostone or limestone. Metal conglomerate, we said in class, comes from conglomerate. All right, so that section helps you with the name of the parent rock, because metamorphic rock are rocks that are existing before and then they were changed. So the original rock is what is called the parent rock. Then the metamorphic rock name is the new rock that was formed as a result of the heat and pressure. All right, next we started looking at the laws of stratigraphy, things that help scientists to tell what happened first, what happened second, and what happened third, and all those other lovely things. I think we started doing that in 2022, January, so we are pretty much done with our review. We're getting pretty close. We looked at various laws. The first law we looked at was the law of superpositioning, which means that the rock at the bottom will be older than the rock that is on top. All right, oldest rock at the bottom, youngest rock all the way on top. Law of superpositioning. The next law we looked at is the law of original horizontality, which means that each rock layer is deposited horizontally, conformably, comfortably, on horizontal plane. So if you see sedimentary rocks that are not horizontal, it means something has happened to skew them or that tilted them, or that folded them, or faulted them, or changed their orientation from being original, but originally they were horizontal. All right, that's what the law of original horizontality simply means. And what can cause rocks to fold? Tectonic plates, movement of tectonic plates, continental drift, crustal movement is all the same thing. The movement of the continent, because of their size and because of the amount of pressure that they have, they can shift igneous rock from being straight, shift them, or cause them to even fold and form a wavy layer. All right. Then if you see a crack on it, what can cause igneous rock or what can cause sedimentary rocks to crack? Earthquake. Yeah, earthquake causes that. When you see a fault, it's caused by earthquake. When you see a fold or a folding, then it's caused by continental movements or continental drift or crustal movement or plate movement. The next law we looked at was the law of crosscutting, which means anything that is being cut through is older, and whatever is doing the cutting is younger. In this case, for example, C will be the youngest because C is cutting through B and A. So C will be the youngest guy here because he's the one cutting through. If C does not cut through anything, then that thing is probably younger than C itself. But if C is cutting through it, then definitely C will be the youngest. Then lateral continuity, I mean, it's just a spin-off from original horizontality, which means it will continue horizontally until something else happens to it. But pretty much, I think that is all that we covered for the law of stratigraphy. So looking at this, for example, in the regent question, you also see this black and white, and then you see that the different layers and the different features will be given different names and different layers. This is a highly complicated one. I don't think you will get anything as complicated as this in the regents, but I'm just putting it there so that you understand from what we did in class and from all our practice, you should have an idea what to expect. So typically you will see that L is an intrusion here. So L is cutting through everything. So definitely around this area, L is much more younger. You see a fourth. This fourth is called an N. So you see that the N is a crack that cuts through everything. So N has to be younger than K, which is this layer. It has to be younger than J, has to be younger than I, has to be younger than H. All right. So, and what could cause N? N is a fourth, remember? So because it's a fourth, it's caused by an earthquake. But you can see that N, however, did not fourth M, which means the crack did not affect M. If you see when the crack went through K, you see how it shifted K. When it went through J, the layer J, you see how it shifted J. When it went through I, you see how it shifted I, it displaced it. This other parts went up, this other part went down. The same thing with H. However, for M, the fourth did not cut through, so M has to be younger than N. So it's important you take note of that. O here is also a fourth, so the same thing applies when you are interpreting that history. Then the last one that we talked about is this squiggly line. I will say those squiggly line represents unconformity. Unconformity is a period where there was no deposition or no production of layers, or is that the layers were produced but something came and washed them away. Erosion came and took them away, such that the sequence was not followed, or there was a gap in communication, or there was a gap in the creation of layers. So that is what an unconformity means. It means it does not conform to the regular pattern that was being observed prior. So it means during this time, something must have came to wash all those layers, and for those layers to be washed off, it means that that part of the earth was lifted above ground, there was an uplift, and it was that uplift that caused rain and weather and different things to wash it off before it was subducted again. So whenever you see an unconformity, it means there was an erosion, and before the erosion could have occurred, there must have been an uplifting. Okay, so that is what an unconformity generally would connote, a time of no production of rock, or a time of erosion, or a time of uplifting. and all that. And then of course, right on top, you can see that this present one around R and S and T, you see that a lot of erosion is already taking place there as well. So it's been eaten into, again, unconformity is already currently happening right on top. So whenever you see a squiggly line in a geohistory setup like this, it just simply represents an unconformity. Then I think this was just a couple of days ago, we talked about index fossils. We said fossils are generally remains of plants and animals that has been preserved for thousands of years, usually above 10,000 years. However, some fossils are regarded as index fossils because they provide bookmark. They connote a definite period of time when those animals or those fossils were created or existed. So for that reason, for a fossil to be considered an index fossil, it has to meet 3 criteria. The first criteria is that it must be widespread, which means it must be found everywhere in the world or in different areas or different parts of the world. Then it must exist for a short period of time, which means it must not be existing forever. And then it must be abundant as well. Okay, then another layer of it would be, it should be easily recognizable or it should be unique. So index fossil needs to meet all these criteria for it to be considered an index fossil. All right, we're going to walk through an example here so you just have an idea how you should go about it. Okay, by abundant we mean a lot of it should be found everywhere, and then by widespread we mean it should be found here, it should be found here, and it should be found here as well. Then by short-lived we mean we only want to see it in one particular layer. All right, that's to be only in one particular kind of layer or kind of rock. So looking at this setup here, what do you think the index fossil is? Yeah, the index fossil is definitely not one, because we can find that this fossil is in different layers. Even though it's abundant, even though it's widespread, we can see it everywhere, but it did not live for a short period of time. How did we know it's not living for a short period of time? Because we can find it here, we can find it here, we can find it here. Let's say, for example, this rock layer, that is layer D, is the Devonian period. This is the say the Permian period. This is the Triassic period, and this is the Cenozoic period. Then we see that this rock has been living since the Devonian all the way through the Cenozoic. So it's not short-lived. It's been living for a long time. So it does not meet the criteria. Number 2, we can see it here. We can see it here. So it's abundant, but it's widespread as well. We see it everywhere, abundant and widespread, but it's not short-lived because we find it in different layers. So definitely not 2. Our answer is 3 because we find it here, we find it here, we find it here, which means it's abundant, it's widespread, and it's only found in one layer, and that is layer C. 4 is not abundant because we only see one of it, so it's not abundant at all. It's not an index fossil. So our correct answer here is 3. Then lastly, we talked about the layers of the earth, okay? And then we say that these layers that are inside the earth were separated into layers because of different density. So the heavier ones sank all the way into the middle, creating the inner core and the outer core. And then you have the mantle, and then you have the asthenosphere, and then you have the atmosphere, which is the earth crust. Good. And then we say that the inner core and outer core are made up of iron and nickel. The difference is that the inner core has a higher density and is solid, but the outer core, however, is liquid with a much lesser density. Mantle, we'll talk about the density shortly, and then we'll talk about the crust. And the crust, we say the crust is divided into 2 parts. The crust is divided into the oceanic crust and the continental crust. And the continental crust is thicker, less dense, and carries the continent, while the oceanic crust is thin, very dense, and mafic. All right. So that brought us to this part of the ESRT, page number 10. Where we talk about the density column. So we see all the density values here, so you should be able to read off what those value is using your ESRT. So we're going to start off with the earth crust. So the earth crust is divided into continental crust and oceanic crust. One has a higher density than the other. Oceanic crust has a higher density. Oceanic crust is mafic, which means it is basaltic, which means it has a darker color, and because of its higher density is always going to be found below the continental crust. The continental crust, on the other hand, has a density of 2.7, and it is thicker, and it is felsic. All right. Then below the continental crust, you have the asthenosphere, and that is the liquid or semi-liquid or plastic part of the mantle where you have convectional current, all right, that we talked about in class the other day. And those convectional currents are represented by this arrow flowing in those directions. So this is the layer of the earth that has the current, convectional current, that pushes the continent or causes the continent to drift apart as we know it today, causing continental drift. Then below that you have the mantle. The mantle has a density of 3.3 to 5.5 grams per cm cube. Don't forget your unit. The outer core is liquid, and it has a density of 9.9 to 12.1 grams per cm cube. And then you have the inner core, equally made up of iron and nickel, just like the outer core, but it is solid with a higher density of 12.7 to 3.0. All right, I think this is where we stopped as of our last class, and it's a good place to end it. We kind of gave definition to lithosphere. We said lithosphere is a combination of the earth crust and the rigid mantle. While we said the mud hole is a discontinuity, it's just like a wedge between the earth crust and the rigid lithosphere. Yeah, I think that's it. So we established that as you go deeper into the earth, density is increasing, as we can see from here. And that is it, ladies and gentlemen. On Wednesday will be our midterm. Hope you saw this review useful to you. I know they are pretty long, but I felt really, me and Mr. Pierre felt really that we need to give you guys multiple opportunities to reacquaint yourself with everything that we've done so far. It's amazing, right? Look how many things we've covered, and we still have a lot to get through before regions. So hopefully this video was useful to you, and we are also going to ask you to come back to this video just before the regions, so that you familiarize yourself with everything we've done for the first term. All right. So why are we learning all this? Because we live on Earth, and Earth is our mother. So let's take care of Earth. Earth gave birth to us. As you saw in geologic history and how life has evolved so far, and human being being the recent evolution in that history. And of course, human being is now the one having the highest impact on the earth, with the whole idea of global warming and carbon dioxide and industry and everything, and all the mess that we're creating on earth. So earth science is really important, that we understand the world around us, understand why we have seasons, understand why our sun is, understand why Jupiter and comets and everything that we've talked about. So Earth is our home. Let's love Earth. And Earth Science love you. Mr. Pierre loves you. Mr. Kennedy loves you all. And I hope you are enjoying the course and the class so far. And here's to wishing you happy success in your midterm. All right. See you guys later. Bye.